quick one for you. You step up to the free throw line 10 times. How many do you think?
Depends entirely on whether it's me or a professional, but some number out of 10. Could be 3, could be 8.
Right, and that some number out of 10 is the whole idea today. You repeat the same yes or no attempt over and over, and you count the successes. It's one of the most common shapes in all of probability. Anytime you do the same yes or no thing a bunch of times and tally how often it works out.
Coin flips, free throws, parts coming off a line, same shape every time. Week 3, Lecture 9, the binomial distribution, and its cousin, the geometric.
Let's build it from the smallest possible piece, a single attempt.
One trial. We capture it with a variable, call it y, and y only ever takes 2 values, yes or no, on or off.
We'll call a success a 1.
And it shows up with probability p. That p is the whole personality of the trial. A fair coin is 1/2. A great free throw shooter might be 9/10. The only other thing that can happen is a failure. That's a 0.
With probability q, which is just 1 minus p. 2 outcomes and the probabilities have to add to 1. So here's a fun little question. What's the average of something that's only ever 0 or 1?
You weight each value by its chance, and it lands right on p. The mean of a single trial is just its success probability, and the spread, the variance, works out to p times q.
Which is biggest when p is 1/2. Makes sense. A 50-50 coin is the most unpredictable trial there is.
And you can read the whole thing right off that little picture on the right. 2 bars, one for failure, one for success, and their heights are just q and p.
One trial is a little lonely, though. The real action starts when you repeat it.
So we run that same trial n times, y1, y2, all the way to yn. 2 rules. Each repeat is independent of the others.
And every one of them has the same p. Nothing drifts from trial to trial. The coin doesn't get tired. The next flip is exactly as fair as the first. So one full run of the experiment is really just a string.
A sequence of zeros and ones. Fail, success, success, fail. However it happens to land. Something like 01101 or 1010.
Every run hands you one of those patterns. And here's the key thing. Nothing gets used up as you go.
Right, it's sampling with replacement. The setup completely resets for every trial. Same 2 outcomes, same p every time. N coin flips, N free throws, N parts off a line. It's all the same skeleton.
The story changes, the math doesn't even notice. But be honest, does anyone actually care about the exact string?
Not really. What we want is the count. How many successes are hiding in there? And that question is what gives us the binomial.
So let's make that count official. Add up all the trials.
Exactly. X equals y1 plus y2, all the way down to yn. Since each y is a 0 or a 1, that sum just counts the ones. X is the number of successes in our n independent trials.
It's pure bookkeeping, really. Every success drops a 1 onto the pile, every failure a 0, and X is just how tall the pile of ones gets by the end. And X can land anywhere from 0 successes up to all n of them.
When X behaves this way, we write it in shorthand. X is distributed B of X, N, P.
Which you just read out loud as X is binomial with n trials and success probability P.
And now the obvious question. What's the probability of exactly X successes? For that, we need a formula.
Here it is, the formula for the whole distribution.
Bo of X, N, P equals N choose X times P to the X times Q to the N minus X.
And that holds for X from 0 up to N, with Q being 1 minus P, as always.
Let's see where each piece comes from. First, N choose X. That's the number of ways to pick which X of the trials are the successes. Think of it like choosing which seats at a table get filled. The order you pick them in doesn't matter, only which ones end up chosen.
Then P to the X, those X successes, each happening with probability P.
And q to the n minus x, all the other trials, the ones that failed.
So any single string with x successes has probability p to the x, q to the n minus x, and there are n choose x of those strings. Multiply, and you've got it. The whole formula is really just two ideas multiplied together: how likely one particular pattern is, and how many patterns there are. Let's actually use it. A fair coin flipped 5 times. What's the chance of exactly 3 heads?
So we're counting heads in n equals 5 trials, with p equal to 1/2. That's x is binomial 5 1/2, and we want x equals 3.
And because it's a fair coin, heads and tails are equally likely. That 1/2 does double duty.
Plug in. P of x equals 3 is 5 choose 3 times 1/2 cubed times 1/2 squared. Notice the two exponents add up to 5, 3 for the heads, 2 for the tails, 1 factor for every flip.
5 choose 3 is 10, and the halves multiply to 1 over 32, so 10 over 32.
Which simplifies to 5/16, about 0.31.
And the intuition. There are 10 different ways to arrange 3 heads among 5 flips, and every single arrangement has probability 1 over 32. Now, we could compute every probability, but often we just want the center and the spread.
For a binomial, the mean is beautifully simple. Mu equals n times p. And it matches your gut. If each of n trials succeeds a fraction p of the time, then on average you pile up n times p successes. And the variance is n times p times q.
With the standard deviation just the square root of npq.
Quick gut check. A fair coin, 5 flips. Mu is 5 times 1/2, so 2.5 heads on average. Feels right.
And why those formulas? Because x is a sum of n independent trials. Each trial contributes p to the mean and pq to the variance. Add up n of them and you get np and npq. The independence is what lets the variances simply add.
For our 5-flip coin, that's a variance of 5 times 1/2 times 1/2, 1 1/4. So a standard deviation a hair over 1 head. The count really does cluster within about a head of 2.5.
Let's see a whole distribution at once. Pick 3 items off a line, each defective with probability 1/4. It's a small enough case that we can just list every outcome and its probability, start to finish.
So we just compute b of x 3 1/4 for every x. 0 defectives is 3/4 cubed, 27/64.
Exactly 1 defective also comes out to 27/64.
2 defectives drops to 9/64.
And all 3 defective is just 1/64.
Those 4 add up to 1, as they must. And the mean, np, is 3/4 of a defective. The picture leans toward few defectives, which is what you'd expect for a small p.
For bigger n, computing each term by hand gets old fast. Nobody wants to add up 15 separate terms by hand, so we lean on a cumulative table.
What it stores is p of x less than or equal to r, the running total of the probabilities from 0 up through r.
You just look up 3 things: the row for n, the column for p, and the value r.
And from that one kind of lookup, you can build anything. Exactly x is p up to x minus p up to x minus 1. Say you want exactly 4. Take the running total up through 4, subtract the running total up through 3, and what's left is just the 4 bucket on its own.
At least x is 1 minus p up to x minus 1.
And between a and b is p up to b minus p up to a minus 1.
So everything reduces to subtracting 2 cumulative values. The only trick is lining up the right r. Quick name for those running totals before we hit the table itself.
Right. They're the cumulative distribution function, the CDF. F of r is just p of x less than or equal to r, the sum of all the bars from 0 up through r.
And if you picture it, it's a staircase. Look at the graph. Flat between whole numbers, then a little jump up at each integer.
And the size of each jump is exactly the PMF bar at that point, the probability of landing right there. Walk to the right, add the jumps, and you climb from 0 all the way up to 1.
So reading p of x less than or equal to r off the table is really just reading the height of the staircase at r.
Exactly.
Slide over to r equals 8 on this curve. Read the height, 0.905. Same number the table hands you. The table is just the staircase written out as a column.
Let's actually find one. Say n is 15 and p is 0.4.
Step 1. Find the block for n equals 15. Step 2. Slide across to the column for p equals 0.4.
Step 3. Read down to your row r, and that entry is p of x less than or equal to r. That's the whole skill. Block, column, row. Do it twice and it's automatic.
So for this example, p up to 2 is 0.0271,
P up to 8 is 0.905.
and p up to 9 is 0.966. 3 lookups, and we're about to turn them into real answers.
Here's the story. Patients recover from a rare blood disease with probability 0.4. Out of 15, X is the number who recover. Part A. What's the chance at least 10 recover?
At least 10 is 1 minus p up to 9, 1 minus 0.966, about 0.034. Rare, as you'd hope to be unlikely. Hope it's likely. You want recovery likely. 10 plus out of 15 is the demanding end.
Part B. Between 3 and 8 recover. That's P up to 8 minus P up to 2. 0.905 minus 0.027, about 0.88. And Part C, exactly 5 recover. P up to 5 minus P up to 4. 0.403 minus 0.217, about 0.19. Same table, 3 different question shapes. And take a look at the bars on the right. That whole distribution is already shaped like a bell. Hold that thought because that's exactly where we're heading. And if you don't have the table handy, GeoGebra's free probability calculator gives the exact same numbers. Pick binomial, set n and p, choose your interval, and read it off. Here it confirms our p up to 9 is 0.966. The buttons for less than, between, and greater than mirror the 3 question types we just did. Now flip the question around. Instead of counting successes in n trials, ask how many trials until the first success. Same coin, same dice, same setup, but now the thing we care about is the weight, not the total.
That's the geometric distribution. G of x, comma p equals p times q to the x minus 1.
Where x is 1, 2, 3, and so on, the trial on which that first success finally shows up.
And its mean is lovely and simple, 1 over p. The variance is 1 minus p over p squared. If success is rare, you wait a long time.
And the picture on the right tells the whole story. Look at those bars marching downward. Each later trial is a little less likely to be the very first success. Let's roll a die until the first 6. Success is rolling a 6, so P is 1/6 and Q is 5/6. A 6 is fairly rare on any single roll, so we expect to wait a bit.
And x is the roll that the first 6 lands on.
So x is geometric with P equal to 1/6. X can be 1, 2, 3, on and on.
Suppose we want the first 6 on the 4th roll. That means 3 misses and then a hit.
So P of x equals 4 is 5/6 cubed times 1/6, which is 125 over 1296, about 0.096.
And the average weight is 1 over p, 6 rolls.
Which is the whole personality of the geometric. You chain x minus 1 failures and then 1 success. Here, 5/6 cubed for the 3 misses, times 1/6 for the hit. Let's pull it together. Today was really about counting and waiting.
The binomial, b of x and p, count the successes in n trials with mean np and variance npq.
And when n gets big, read those probabilities straight off the cumulative table.
Plus the geometric, the weight for that first success.
And next time, more distributions. 2 more discrete families round things out. the negative binomial, and the hypergeometric.
And then we cross over from bars and counts into a smooth, continuous bell curve.
That's Lecture 10, the negative binomial and the hypergeometric. And then the star of the show, the normal distribution. See you there.